All right, here's our next in-class video for Math 132 during this online teaching. This video covers section 4.1, part 2, which is stuff about sigma notation, as well as section 4.2, which is definite integrals. The sigma notation is video 2. This is chapter 4, section 2, video 2 in the pre-class videos by Ryan. So first here, our first couple of examples are working with sigma notation. This first example is your web work 4.1 part 2, number 4. And the way that we're going to do this one is because these indices are so close together, we're just going to plug in 2, we're going to plug in 3, and we're going to plug in 4. And then we're going to go ahead and just add those all together. This is called a finite sum, and we can do it by just plugging in those values. So we're going to plug in a 2. We're going to plug in a 3, and we're going to plug in the 4. When we plug in the 2, we get 3 times 2 over 2 plus 1. When we plug in a 3, we get 3 times 3 over 3 plus 1. And when we plug in a 4, we get 3 times 4 over 4 plus 1. And if we go and simplify those one step, we get 6 over 3 plus 9 over 4 plus 12 over 5, and that's totally okay for our final answer because we don't need to simplify here. Now for this next example, this is WebWork 4.1 Part 2, number 5. This is an example where we can follow a pattern here that's happening with the sum. So let's go ahead and write out the first couple of terms. So if we plug in a 0, or if we plug in a 1, or if we plug in a 2, or if we plug in a 3, what happens here? We start adding these together. So we're going to get the cosine of 0 plus the cosine of pi plus the cosine of 2 pi plus the cosine of 3 pi plus, we can use this dot 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 to represent that. Eventually we're going to plug in a 92 up here. So we're going to get the cosine of 92 pi. If we go ahead and evaluate these cosine functions, we get 1 plus a negative 1 plus a positive 1 plus a negative 1. And our last term here is going to be a positive 1. And then if you notice, we can pair off each one of these terms, and we get 0 with each odd even pair. And then at the very end here, we can expand this a little bit more. We're going to have the cosine of 90 pi plus the cosine of 91 pi plus the cosine of 92 pi. And we're going to get a 1 minus 1 plus 1 here. So this is going to be our last 0 pair, the 90th and the 91st. And so every term zeroes out except for this very last one. And therefore, our answer is just 1. Yeah, that one's a trick. We're just going to use pattern recognition to complete part B. Now for part C, we have a infinite sum or an undefined sum because we have n here in our variable. So we're actually going to need to use something from the other lecture videos. Let's go and take a look at those notes really quick. So chapter 4, section 2, video 2, these are Ryan's videos. At about 8:30 in the video, he fills out theorem 2.5 here, which tells us how to find sums with n as the second quantifier of different functions, the constant function, I and I squared. Note that if we add from 1 to n a bunch of 1s, we get n times 1 because there's n 1, so we get n. If we add I a bunch of times, we get n times n plus 1 over 2. We're going to use these two equations for our problem. So let's go back to our problem. So what we have here is we can use the properties of summation to split the summation up. So we can do the sum I equals 1 to n of 4i minus the sum I equals 1 to n of 3. And then we can pull out some constants here. So we can pull out a 4. We have the sum I equals 1 to n of I, minus, and we can pull out a 3 here. We have the sum I equals 1 to n of 1. And now we can use those two equations from our videos. The summation of I from 1 to n is n times n plus 1 over 2. And the summation of 1 from 1 to n is just n. So these are two things that we substituted in right here from that theorem in the second video of the 4.2 notes. And we can simplify this a little bit. So we get 2 times n plus 1 minus 3n. And so that's 2n squared plus 2n minus 3n. And that just gives us 2n squared minus n right there as our fully simplified final answer. So now what we could do is, if we ever knew what n was, instead of adding up the summation of all the terms, we can just plug in our n to our closed form simplification there. So this is using theorem 2.5 from the chapter 4 section 2 video 2 notes right there. Let's go and take a look at the last problem here on this page. Now what we're going to do is we're going to sum up this exact same sequence that we did in part C, but our n is given to us. N is 106. So all we need to do is we need to plug in 106 into our summation. And when we do that, so if we plug in 2 times 106 squared minus 106, we get 22,366 there as our final answer. And we could do that so easily because we had our closed form summation here from the previous example. So as we scroll into our next example here, we're going to see that we need to evaluate the integral by interpreting it in terms of area. You should be thinking, when you see this phrasing, interpreting it in terms of area, this means that we're going to use geometry. So the first thing that we're going to need to do for any of these problems is we're going to have to graph the integral and the integrand. So here we have the integral from -3 to -2 of x plus 1. So I need to make sure I graph y equals x plus 1. So there's my y equals x plus 1. And I need to make sure that I have this graphed from -3 to -2. So I need to continue my line there. And we know that this is going to intersect at 1 and -1. And then we know down here at -2, when we plug in a -3 into this equation, we should get a -2. So this point right there should be the point -3, -2. Now, the area that we're trying to calculate is this area right here. And that area is, let's go and write this a little bit differently. We'll write this over here as our little trapezoid. And I'm going to go ahead and subdivide this. We have a width here of 1, and this total height right here is 2, which means that this height must be 1, and this height must also be 1. Therefore, we have area 1 inside of this little square, and area 1/2 inside of this little triangle right here by doing 1/2 base times height. And that tells me that my integral is -3/2, because I'm doing 1 plus 1/2. My area in here is 3/2. But since this area is underneath the x-axis, the sign of our integral should be negative. So our integral here is -3/2, even though the area itself is 3/2 inside of there. When we're finding the integral, we have to think about the area having a sign. So when it's below the x-axis, the sign of this area is negative. Let's go and take a look at this next example. So this next example is an absolute value problem, and we know that 2x minus 6 is equal to 0, x equals 3. So our little horn of our absolute value function is going to be at x equals 3. So we need to go ahead and sketch a graph of this. So 1, 2, 3, 4, 5. Our integral is going to be from 0 to 4. This function is going to hit at x equals 3. And if we plugged in a 4 right here, we get 8 minus 6. That is a positive 2 up there. If we plugged in a 3 right here, we get 6 minus 6, that's our 0. If we plugged in a 2, we get 4 minus 6, that's a negative 2, but then we take the absolute value. If we plug a 1 in there, we get 2 minus 6, that's 4. We need to add some more ticks to our graph here. So f of 1 is 4, f of 0 is 6. Oops, that wasn't at 4, that was at 5. There's our 4 right there. So our graph looks something like this. We're trying to find the area underneath this graph. So we have two triangles here. This triangle, it's the area of a triangle, should be 1/2 base times height. In this case, the base is 3 and the height is 6. So we end up with an area of 9 for the big triangle. And the area for the second little spot, the second little triangle right there, is going to be also 1/2 base times height. But in this case, our base is 1 and our height is 2. So our area in there is 1. And the total area that we have then is positive 10 because we are above the x-axis. So both of these problems, the first two examples, used rectangles and triangles to calculate the area of shapes that are straight like polygons. For part C, you have to use your creativity a little bit. Now what does this function square root of 9 minus x squared look like? Y equals the square root of 9 minus x squared. Well, if we square both sides, we get y squared is equal to 9 minus x squared. And if we add the x squared over, we get y squared plus x squared is equal to 9. And I could rewrite that as y squared, or I could rewrite that as x squared plus y squared is equal to 3 squared. And this fits into our circle equation, which is x minus h squared plus y minus k squared is equal to r squared. And this is the equation of a circle with a center at hk and radius r. So our circle that we're dealing with is centered at 0, 0, the origin, and the radius is 3. So we have a circle that looks something like this. 1, 2, 3, 1, 2, 3, 1, 2, 3, and it actually is only the top half of this circle. And the reason why is because if we went backwards and we started with our circle equation, when we take the square root in between this step, we would have to do the plus or the minus square root. But our original equation is just the plus part of the square root. So we're just dealing with the positive side of the circle here. So it's just a semicircle above the x-axis. And now what we need to do is we need to find the area from 0 to 3, which is this area right here. That is a quarter of a circle, and a circle has an area of pi r squared. So our area is going to be 1/4 times pi 3 squared, which is just equal to 9/4 pi. So the answer to this problem is 9/4 pi by using the area of a circle. All right, hopefully that made sense. So I'm going to give you a second to jot down those notes, and then we'll go on to the next example. All right, on the third page of the notes here, first we're going to fill out a theorem. So if we're finding the integral of f plus g, that's the same thing as the integral of f plus the integral of g. So we can just add areas together. If we're finding the integral of a constant times a function, that's the same thing as that constant times the integral of that function. So it's a linear operator. We can pull constants out. The integral of a constant function is just going to be the b minus a times k. That's because this is just a constant. What's the area underneath a constant? Well, the constant is the height, and then the width of the rectangle is b minus a. If we flip the bounds of the integral, it just makes the integral negative. And we can add two integrals together so long as their integrands are the same. And you can see here that what's happening is that we're adding the integral from a to b with the integral from b to c, and that equals the integral from a to c. So I'm going to graph that last one. This is pretty obvious, but it makes a lot more sense when we see it on a graph. So if we have some function here, if we're going to take the integral from a to b and then the integral from b to c, this first area right here is the integral from a to b of f of x dx, and the second integral, or the second area right here, is the integral from b to c, not b to b, the integral from b to c of f of x dx. And so when we add those two integrals together, we could have just found the integral from a to c of that function, because we can add integrals together. Now what we're going to do is we're going to use these integral properties to answer a question where we're given some definite integrals, or we're using that to find other definite integrals. All right, for example 18 here, what we're going to do is we're going to need to break down this integral so that we end up with just f's and g's on the inside. So first of all, we can use our properties to say that this is 2 times the integral from 1 to 7 of f of x dx minus the integral from 1 to 7 of g of x dx. And then we know that the integral from 1 to 7 of f of x is equal to -1, so we know that the beginning part of our answer is 2 times -1. Now, we don't have the integral from 1 to 7 for g, but we do have the integral from 1 to 3 and then 3 to 7. So we could rewrite this integral from 1 to 7 as being the integral from 1 to 3 of g of x plus the integral from 3 to 7 of g of x. And then that tells us that we get 2 times the -1, which is just -2, minus the quantity 7 plus 10. So we get -2 minus 17, and our complete total integral here is -19. Now, if you'd like to pause the video, example 9 in your 4.2 web work is very similar to this example. So why don't you go ahead and try that, and then come back and you'll see how I do these two examples. Alrighty, for part A here, we're trying to find the integral from 13 to 16 of f of x. And I'm given the integral from 10 to 19, 10 to 13, and 16 to 19. Somehow I got to get from 13 to 16. Well, one way to do this is by just using the theorem exactly as we see it. So we're going to want to do the integral from 13. The only one that I know is 10. So we're going to start with the integral from 13 to 10 because I know that the integral from 10 to 13 is 18. So you know this part of my answer is -18 then. Now I'm going to have to, my end point of my first integral was 10, so that has to be the starting point of my second integral. And if I go from 10, I can only go to 19. So I need to go to 19 there, f of x dx. And then my last integral will be from 19 to 16. So I went from 13 to 10, 10 to 19, 19 to 16, and that resulted in going from 13 to 16 overall. I need to finish. This is f of x dx. And now I can go ahead and substitute in all of my answers. So from 10 to 13 is 18, which means 13 to 10 must be negative 18 because I have to flip it. 10 to 19 was 2. And 16 to 19 is 7, so 19 to 16 is negative 7. If I add these all together, I get negative 25 plus 2 is negative 23. There's another way I could do part A as well. One way I like to do it is I know that the integral from 10 to 19 is positive 2. The integral from 10 to 13, let's make that a little bit shorter, I guess. 10 to 13 is positive 18. And the integral from 16 to 19 is positive 7. So what I'm looking for is I'm looking for this integral from 13 to 16. Well, what number must need to go here in order for 18 plus that number plus 7 to be equal to 2? So we have 2 is equal to 18 plus some number that we don't know plus 7. So 2 minus 18 minus 7 is equal to our answer, and that is exactly going to give us negative 23. So a couple of different ways that we can think about that. But negative 23 is the answer that you need to get for part A. Now for part B, we need to do the integral from 19 to 13 of f of x dx. Okay, well, I know that the integral from 13 to 19 is given by the integral from 13 to 10 of f of x plus the integral from 10 to 19 of f of x. And the integral from 13 to 10 is negative 18, and the integral from 10 to 19 is 2, and therefore my answer for part B is negative 16. So this page was pretty much just playing around with some of the known definite integral formulas. Give you a chance to write down some of those notes, and then we'll go ahead and move on to the next example. All right, let's take a look at the next example. These final two examples are by far the hardest examples in section 4.2, and they're really, really tricky because what we're doing is we're using the Riemann sum to actually calculate the integral. And so that's the idea from section 4.1, where we were using Riemann sums to approximate definite integrals. Now we can use Riemann sums to actually calculate a definite integral by using n going to infinity number of rectangles. So if we use an infinite number of rectangles in our Riemann sum, we'll be able to calculate the area exactly. All right, another piece of information that we're going to need to know here is that the integral from a to b of f of x dx can be calculated by taking the limit as n goes to infinity of the Riemann sum I equals 1 to n of f of x to the c times delta x. That is very confusing. What is going on here? What we're saying is that if we find the integral of some function from a to b, what we're trying to do there is we are trying to find the area underneath that curve, and the way that we're going to do that is by using Riemann sums. So if we go ahead and take the right-hand endpoint here, we're going to put all of these rectangles on this curve by plugging in the right-hand endpoint and finding the height of each of these rectangles, and we're going to approximate the area using a finite number of rectangles. What this is saying is that we can use an infinite number of rectangles and that we should get exactly the area. Now there's a couple of other things here that we'll need to know. Delta x is equal to b minus a over n. All this is saying is that we have the width of the interval divided by n. That's going to be the width of one of these rectangles. So this width right here is delta x. So there's the width of one of our rectangles. And then x to the c right here, that's equal to a plus I delta x. Now what's the deal with that? Well, if we have an interval here from a to b, and it's split into n subintervals, now what we want to figure out is our x sub c's, these are going to be the right-hand endpoints. So we're going to take this endpoint, find the value, that's going to be the height. We're going to take this endpoint, find the value, that's going to be the height. So what we want to do is we want to figure out how do we find the endpoints of rectangles. Well, let's say that we were just trying to do this for 5 rectangles. 1, 2, 3, 4, 5. So what we'd want to do here is first we'd want to figure out that our delta x is equal to b minus a over 5. And that's saying that this jump right here, that's 1 delta x. This is 2 delta x's. This is 3 delta x's. This is 4 delta x's. And finally, that's our 5th delta x. It takes 5 delta x jumps to get from A to B. And so all this is saying is that the endpoint for any given rectangle is going to be found by taking your starting value A, and then we're going to jump over I times. So the 4th rectangle here, we're going to do 4 delta x jumps. So we're going to jump over I times delta x times, and that is going to be the endpoint that we're going to use to find the height of that particular rectangle. So we're going to take that endpoint and we're going to plug it in to our function. So what we're going to try to do in this problem is do that process in reverse. We can see here that delta x is equal to 2 over n. That tells me that b minus a is equal to 2. That's the numerator right here. So if a is equal to 0, that must mean that b is equal to 2. Alright, so let's take a second and let's rewrite our summation. So we have the limit as n goes to infinity of the sum I equals 1 to n of 7 plus 2I over n cubed. And now I know that my 2n is my delta x. And that tells me that this thing right here, the 7 plus 2I over n cubed, that must be my function value. Those must be the heights of my Riemann rectangle. So I know that f of x of c is equal to 7 plus 2I over n cubed. What I'm trying to figure out is what is f of x? What is the function that is the integrand of my definite integral? I'm going to need to go back and calculate my x sub c value. Remember, x sub c is a plus I delta x. So in this case, x sub c is equal to 0 plus I times 2 over n, or x sub c is equal to 2I over n. So that tells me, if I look back at this x sub c function, that I have 7 plus x sub c cubed, and that just tells me that my function is 7 plus x cubed. And now I can use my a and my b values and my function that I just found, and I get that this sum is finding the area of the integral from 0 to 2 of 7 plus x cubed dx. Alright, that was a little bit confusing because we had all the extra explanation in there. Let's go ahead and do this a little bit more simply for part B. So to recap, we know that delta x equals 2 over n, and that tells us that b minus a over n is equal to 2 over n, which tells us that b minus a is equal to 2. Basically, the numerator on the very outside here, the 2 over n, that 2 gives us the width of our interval. So we know right away that b is equal to 9. Okay, now we can calculate that x sub c is equal to 7 plus 2i over n, because we have a plus I delta x. Our a in this case is 7, and our delta x is 2 over n. So if we have 7 plus I times 2 over n, we get 7 plus 2i over n. Okay, so we know that f of x sub c is equal to 7 plus 2i over n cubed. Looking back up to the original problem, this is our delta x, this is our function. That's the exact same step here. Our function is the height of our rectangles. These are the widths of our rectangles. So that function is still the same. But now, notice that our f sub c value is just the thing that's being cubed. So f of x sub c is just x sub c cubed, because that thing is x sub c. And that tells us that f of x is just x cubed, because we moved our integration by 7. Therefore, our final answer is the integral from 7 to 9 of x cubed dx. All right, weird example there. Let's just go ahead and finish these examples on this page with this last set of these Riemann sum things. All right, this is 4.2, number 2 on your web work right there. So we're going to do the same kind of thing. Basically, our answer here is going to be, we're going to have some integral, and we need to figure out what integral this sum represents. So the steps here. First of all, you need to figure out that delta x is equal to 3 over n. That's given right there. And that tells us that b minus a is equal to 3. So the width of our integral is equal to 3. So it might be the integral from 1 to 4, or it might be the integral from 2 to 5, or something like that. But what we know to start with is that the width of the integral is 3. Second, we know that the function that we're plugging our endpoints into to find our heights is the other part of the equation. This is our function. So our function is 2 over 5 plus 3i over n. That's our function x sub c, if we are keeping our notation constant. Now there's really two possible obvious solutions. We can either have a equals 5 or a equals 0. And both of these solutions will yield different answers, but they will both be correct. So if a is 5, that means that x sub c is equal to 5 plus 3i over n. And therefore, f of x sub c is equal to 2 over x sub c, because we can directly substitute the entire denominator, which tells us that our function here is 2 over x, and that tells us that our integral is from 5 to 7 of 2 over x dx. So that's one possible answer. If we had a being 0, that would tell us that our x sub c is equal to 0 plus 3i over n. And then so our function f of x sub c is going to be 2 over 5 plus x sub c, because this is just 3i over n. We'll be substituting for 3i over n there, and we'll have that 5 left over. So then our function, our integrand of our integral, is 2 over 5 plus x. And then our integral is from 0 to 2 of 2 over 5 plus x dx. Both of these answers are equivalent, actually, and they're both the correct answer to this particular question. And that's all we're going to do for 4.2. Please don't worry too much about the last page of these notes where you're using these infinite sums to calculate integrals. Remember that from now on, we're basically only going to need to use geometric areas like we did in the second page of the notes here, where we used areas to calculate integrals. And then right away in section 4.3, our next lesson, we're going to learn how to use a fundamental theorem of calculus, which is using antiderivatives to calculate integrals. So all of this work here at the end of the notes, where we were doing this crazy Riemann sum stuff, basically you just need to get through your web work on this stuff, and then you don't need to worry about it again, because this is kind of the work beneath the fundamental theorem of calculus. That's all for today. Have a great day.